Hey guys, thanks for tuning in. In this video, we're going to talk about using a change of variables to help us compute a double integral. So what we'll start this video with is an example of a double integral that we already know how to set up in xy space, but maybe we don't really want to compute as a dy dx integral. So for example, let's use a double integral to calculate the area of a circle of radius 4 that's centered at the origin. So we know the equation of a circle of radius 4 centered at the origin. It's x squared plus y squared is equal to 16. And of course, you could solve this equation for y to say y is equal to plus or minus the square root of 16 minus x squared. And now we have a y top and a y bottom. And we know that x is going to range from -4 to 4, and we can use that double integral to compute the area of this circle. By the way, I realize that it's kind of pointless to use a double integral to compute the area of a circle when we already know that the area of the circle is given by pi r squared. But this is going to become a more useful technique later, because once we know how to do this, once we know how to do a change of variables for this simple calculation, you could start throwing in an integrand other than 1 and compute some interesting double integrals that cannot be computed using pi r squared. All right, so where are we at with this? We have successfully set up a double integral that expresses the area of our circle. However, we have a double integral that we don't really want to compute because it ends up being really difficult. So let me show you. First, I need to unpack this dA real quick. You guys know what dA means. It means with respect to a small change in area. So you can imagine your dA being a small little rectangle. And that rectangle is spanned by a little dy and a little dx. So dA is equal to, you could write it as dx times dy or dy times dx. More often than not, I'll do dy first and dx second, just because it's more familiar for me. Either order is going to work. Anyway, that allows me to rewrite my double integral as you see on the lower left of the screen here. All right, so let's talk about number crunching. The drawback here is that this double integral is actually pretty difficult to evaluate, especially considering we could just do pi r squared for r equals 4 to find the area of this circle. So we don't know a top 20 from our Calc BC class last year. We don't know an antiderivative that we've memorized from last year to help us here. Now, is there an antiderivative we can use? Yes, we can memorize more formulas to compute this double integral, but that doesn't seem like a great way to go about learning calculus, memorizing more and more antiderivatives. That's kind of fallen out of fashion in recent years, possibly because of the advent of technology, moving more towards understanding concepts than memorizing antiderivatives. So the first step here, getting from the double integral to the single integral, that's straightforward. You guys can all do that. But here, this next step, this is not something that we want to have to do from memory. And honestly, I don't even want to just plug it into Mathematica and have Mathematica compute that antiderivative. I want a better conceptual approach to this problem. So you do get 16 pi because if you do pi r squared for r equal to 4, 4 squared pi is going to be 16 pi. So anyway, this is a bit of a mess. There's got to be a better way to utilize integration in a more clever fashion to get the result that we're looking for. And so the first question that I always ask when I'm introducing this material is, was there a better coordinate system? We were working with rectangular coordinates. We were working in xy space with rectangular coordinates to find the area of a circle. And it seems like maybe that's not the best approach, because if our region is a circle, but our coordinate system is rectangular coordinates, maybe we have a little bit of a mismatch there in terms of optimizing our integration step. So what coordinate system would we prefer to go with? Think about it for a second as I transition to the next slide. And you're right, we would want to try polar coordinates. That might be a better direction to go in. So let's try polar coordinates here. So I know how to parameterize this circle, hence I know how to write x of rt is equal to r cosine t, y of rt is equal to r sine of t. So let me go ahead, and you also can go in the other direction, right? You could reverse polar coordinates using this r of xy and t of xy. You don't see it come up as much in this course. Typically, we're going to see this r cosine t and r sine t as the main the main parameterization we're going to be working with, the main mapping between xy space and RT space. All right, so in this coordinate system, our region R it's really elegant to describe our circle, right? Because our circle is just R goes from 0 to 4, and T goes from 0 to 2 pi. And so if we really naively apply this to our double integral, we're going to make a mistake here, but we have the right general idea. So the area of our region R, the area of our circle, is the double integral of 1 dA. And let's try writing that as the double integral where R goes from 0 to 4 and T goes from 0 to 2 pi. So R from 0 to 4, and then T from 0 to 2 pi. We're just kind of matching up what we see here with our parameterization, the bounds for our parameterization. Now, if you guys noticed that I was getting kind of picky early on in this course about when you parameterized a region, I was pretty picky about making sure that you gave bounds for that parameterization. The reason I was picky with that is because the bounds of our parameterization turn into our limits of integration when we start double integrating. So there was a reason I was picky with that. That habit is now going to serve you well in this chapter. But we do have an issue. I said something kind of dangerous here where I just replaced dA with dr dt without being very careful about it. I colored it in red just to kind of warn you that we have a little bit of an issue here. If we go ahead and compute this double integral, we get 8 pi. And that's a big problem because we wanted 16 pi. So something went wrong. We made some sort of assumption that brought us down a dangerous path. Let's try to figure out what it was. And mainly what was going on is that we said that dA is equal to dr dt, but that's not true. dA was dx dy. dA is something that exists in xy space, and it's a small change in x times a small change in y, or vice versa. But dr dt doesn't really fit with that. So we have a little bit to fix. However, we saw some good things going on. So the thing that I liked about this setup, that I have to fix it, but I saw some promising signs. For example, I really like that this double integral has numerical limits of integration, because it kind of looks like what I started with was a double integral over a circular region, and now when I see a double integral with numbers, with constants for the limits of integration, I kind of think of integrating over a rectangle. So it's kind of like I moved my integral from a space where I was integrating over a circle to a new coordinate space where I was integrating over a rectangle. And it turns out that's exactly what I'm doing. In xy space, my region is a circle, but in RT space, my region is a rectangle. And it turns out that my parameterization is a mapping between my two coordinate spaces. You maybe didn't think about this think about it in this way when it was first introduced at the beginning of the school year, but we learned how to parameterize curves and we learned how to parameterize surfaces earlier in this course. And when we were doing that, what we were actually doing was finding a way to map between, say, our circular region in xy space to a rectangular region in RT space. A parameterization is a change of variables, a change of coordinates. So here it is. This parameterization, x of RT equals r cosine t, y of RT equals r sine t, is a map between a rectangular region in RT space and a circular region in xy space. A parameterization is a change of coordinates, a map between coordinate spaces. Now, I color-coded this so that we can start to see some interesting correspondences between these pictures. By the way, this mapping is invertible, so you can go in both directions. You could start on the RT rectangle and map into the XY circle, but you can also start in the XY circle and map back into the RT rectangle as well. Now, the direction that we're going to concentrate on is this one, the r cosine t comma r sine t. Let's look a little bit closer into that. So let's look at this blue line that we have right here. Now, anywhere on this blue line, I have an r-axis and a t-axis here. So anywhere on the blue line, I have r is equal to 4, and t is allowed to vary along this blue vertical line. T varies from 0 to 2 pi. Well, let's think about how this blue line maps from this RT rectangular region into this XY circular region. So you can kind of think of this as taking your x of RT equals R cosine of t. You could think of plugging in R is equal to 4 and then letting t vary from 0 to 2 pi. Well, that would be 4 cosine t as t varies from 0 to 2 pi. We could do the same thing for the y-coordinate. Our y of RT is equal to 4 sine t. And so again, imagine, or actually I guess technically I've got an r here, and I want you to imagine plugging in r equals 4. So my y of RT is r sine t. Imagine plugging in 4 for r and allowing t to vary from 0 to 2 pi. Oh, guys, that's just the parameterization for a circle of radius 4 centered at the origin. So this vertical line in RT space maps into this circle of radius 4 in XY space. We could try a couple more. So now let's try the green line. So let me clean up a little bit here. And for the green line, what do we have going on? Well, for the green line, R is allowed to vary from 0 to 4, but t is fixed at 2 pi. So you want to imagine plugging into r cosine t and r sine t. Well, t is going to be fixed at 2 pi, so you want to imagine plugging 2 pi in for these t values, and then allowing r to vary from 0 to 4. Well, you can see I kind of did the work here. We know that sine of 2 pi, that's going to give us 0, while cosine of 2 pi is equal to 1, so I didn't even write it here because 1 times r is still r. So what do I have happening? I have r varying from 0 to 4, while my y value is fixed at 0. Well, here it is. That line segment has r varying from 0 to 4, or my x value varying from 0 to 4, and my y value fixed at 0. And we could try this, for all these different colors. So let's keep moving. So the orange line, if you look on the right-hand side, it looks like it's missing. Where's orange, right? You see it over here. The orange line is where t is fixed at 0, but my r is allowed to vary from 0 to 4. So you can see I have r varying from 0 to 4, but t is fixed at 0. And oh, I guess that just maps into the same line segment. So the orange is right here. It's just underneath the green. And then finally, we can look at that red line. Red line's interesting. So this red line over here, remember we have RT space and RT axis. This is fixed at r equals 0, but t varies from 0 to 2 pi. Well, if you have r cosine t and r sine t, where r is locked in at 0, both of those are going to end up at 0. So this whole line segment maps into the origin. All right, so hopefully this gives you an idea of how we can think of this parameterization r cosine t comma r sine t as a transformation between two coordinate spaces, a map between an RT rectangular region and an XY circular region. We never really thought about parameterizations in that way before, but that's what's going on. Now, one thing that you might want to do is maybe pause the video and try a couple points yourself. So you might want to say, okay, I'm just going to do this for a single point, not an entire line segment. Maybe I'll just, pick something like 3 comma pi over 2. Let's see how that point maps from my RT rectangle into my XY circle. And so you would just do this. You would say, okay, my x of RT and my y of RT is going to equal, I have r cosine t and r sine t, but in this situation, my r is fixed at 3, so I'll put some 3's in there. 3, 3, 3, and 3. And then my t is fixed at pi over 2. Maybe I'll change colors here. Try not to erase too much. So let's change ink colors. Pi over 2, pi over 2, pi over 2, pi over 2. And I'm going to leave it for you to calculate these and figure out which point in XY space I map into. I think that's good practice. Maybe try that for a few points. Feel free to try some easy ones. Maybe pick things where you do have some unit circle values. I'd much rather calculate 3 cosine of pi over 2 and 3 sine of pi over 2 than I would, 3 cosine of pi over 7 or something, right? All right, so now let's think about what's happening here as we map between our RT space and our XY space. So we have something interesting happening. Look at this mapping here. I have a few examples of rectangles of fixed size in my RT space, and then the little sectors that they map into in XY space. So look at this. Sometimes my RT rectangle maps into a tiny little piece of area in XY space. Now, here's another rectangle of the same exact area, and that seems to be mapping into a sector in XY space that's about the same area as what I had in RT space. And then again, another rectangle in RT space that's the same area as the others. But look at this, it's mapping into a huge sector in XY space. So what I'm noticing about my transformation, what I'm noticing about my mapping, about my parameterization, is that for a rectangle of a fixed size in XY space, when I map it into when I have a rectangle of fixed size in RT space, when I map it into XY space, the amount of area seems to be changing, right? This is called a non-area preserving map. My transformation is a non-area preserving map because sometimes I map into an XY sector that's the same size as the original. Sometimes it's way larger, and sometimes it's tiny, it's way smaller. So that's really where we ran into issues at the very beginning of this PowerPoint. When we tried to do that double integral as the double integral of 1 dr dt, what we were not accounting for was the fact that our parameterization, our mapping between coordinate spaces, was non-area preserving. That's what we're going to have to adjust for. And then the technique you saw at the beginning of the slideshow is going to start to work once we have our adjustment factor. So what we kind of want to zoom in on now, what we kind of want to hone in on, is thinking about how a small change in area in our rectangular region translates to a change in area in our circular region. And if we can kind of pinpoint that, if we can kind of figure out some mathematics to handle that non-area preserving map, I think we're going to be in pretty good shape. All right, so what I want to do is think on a very small scale here. I want to imagine a really small rectangle in the RT plane. I'm going to start it at the point r comma t, and I'm going to make this small little rectangle in RT space have a base of delta r and a height of delta t, just to kind of indicate that it's really little. And so under our transformation, I'm going to call the transformation t of RT. It's really just our parameterization, right? For polar coordinates, we just have r cosine t comma r sine t. That's just our way of mapping this rectangle into part of our circle in XY space. But let's use our transformation, and we can imagine that as a small little sector of area in XY space. Now, for something other than polar coordinates, we can imagine this shape looking a little bit different, but let's think about polar coordinates right now, because I think that's probably something that we're all somewhat familiar with, and I think this piece of a sector is probably something that's easy for us to picture as we're doing our mapping, especially since you just saw the slide with that animated GIF where we were going back and forth. All right, so I'm going to pinpoint my vertices. I'm going to say, you know what, if I want to figure out where this rectangle goes, probably the best thing to do is look at the vertices of that rectangle and see the points that they map into. I mean, you could kind of see the points that they're going to map into because we could see the result of those vertices in XY space. So let me put some labels in here. So for my labels, I've got my starting point of r comma t, and then my other vertices are you just get those by adding the base and the height, right? If we're just thinking of this in terms of coordinates, the point on the right here is r plus delta r comma t, and you could do that for all 4 vertices. Now, how do those 4 points map into XY space? You just apply your transformation. So my transformation is x of rt comma y of rt. This is our way of figuring out, given a particular r and a particular t, what point x comma y is associated with that in XY space. So you could see it happen here, right? Like this point r comma t goes to x of rt comma y of rt. And then I could kind of change colors here. I'm not going to show you, I'm not going to highlight all of these, but r plus delta r comma t maps into the point that you see here, x of r plus delta r comma t comma y of r plus delta r comma t. All right, this is starting to get kind of complicated, so I'm going to try to clean it up in a minute. So I'm going to try to clean these guys up here by, instead of writing it in terms of the right side of this equality, I'm going to write it in terms of the transformation, just because I think that's going to make everything look a little bit cleaner. Maybe is a little bit more abstracted that way. What I like about how it's currently written is this is literally how you would figure out where these points are mapping. You'd plug into your parameterization x of rt comma y of rt. But you could see how small I had to make the font size to make this work. So let's just use the notation on the left side, this transformation notation. There it is. Yeah, that looks a little bit cleaner. All you have to remember, though, is this t of r comma t plus delta t, that's some point x comma y in xy space. And that's true for all of these. These are each just some point in xy space, some ordered pair. So try not to have it be too abstract in your brain. Each of those vertices that we've mapped into xy space are just an ordered pair in xy space. Now, what I notice here is if I want the area of my rectangle on the left-hand side, that's really easy to compute this area. So my area, I'm going to call it delta ART. My change in area in RT space is given just by delta R times delta T, right? Base times height. So as I change delta R and delta T, I could see how my area changes in RT space. It's just delta R times delta T. However, that's not a particularly useful observation. It was an easy calculation, but it's not particularly useful because remember, if we go back to the very beginning of this PowerPoint, what was I trying to do? I was trying to compute a double integral in XY space. So I really care about my XY region, my double integral dy dx or dx dy, and not so much how much area I have in RT space. So this guy's easy to compute, not very useful. Instead, here's what I actually want. Here's the quantity that I'm trying to hone in on. I want a change of area in XY space. Basically, I want to know how much XY area results from doing our calculation in RT space. So what I want to do is I want to integrate over here in RT space, but I want that double integral to tell me how much area I have in XY space. That's what I'm really trying to hone in on. The good news is we have a way of trying to approximate how much area we have in XY, right? We basically need the area of this XY region. We know the area in the RT region. We want to know how much area does that translate into in our XY region. And our trick for doing this is to draw a parallelogram. So what I'm going to do is I know these 4 vertices of my region in XY space. I'm going to just kind of connect the dots. I'm going to make 2 vectors like this. Let me show you what they're going to look like. I'll have them animated better in the video, but I'm going to make a vector here and a vector here. And then I'm going to use that to span a little parallelogram. It looks something like that. And that parallelogram is not perfect, but it'll be a pretty good approximation of how much area I have in this little XY sector piece that I have here. So the gray area is going to be approximated by the area given by a parallelogram. So here's the first vector, and there's the second vector. How do I get those 2 vectors? I'm calling them V and W, by the way. Nothing special about those names, just a placeholder in case I need more compact notation later. Well, you guys know how to find a vector, right? If you have a point P in space and a point Q in space, if I want to find the vector from P to Q, that vector is just, you just do Q minus P, right? You just take your tip minus your tail, and that's going to give you your vector. And that's what I did on the slide. I just did tip minus tail, right? If this guy's the tip of a vector, it's just some xy coordinate. And if this guy's the tail, if I do tip minus tail, that's my vector v. You could do the same thing for the green one, w. Now, once I have those vectors, I could figure out the parallelogram spanned by those 2 vectors, and it's the orange parallelogram you see there. Now, is the orange area exactly the same as the gray area? No, but you could see they're pretty close. I mean, there is error, right? You could see some error here, but are they pretty close to each other? Sure. All right, so let's try to figure out the area of the orange parallelogram, and then let's try to justify to ourselves that it's useful to find the area of this orange parallelogram. So here's what we do. Here's our vector v, and I'm going to do a little bit of an algebra trick here. I'm going to take my vector v, and I'm going to multiply and divide by delta r. I know that delta r is some non-zero quantity, and so I can multiply and divide my expression by delta r over r. Now, this looks a lot like the limit definition of a derivative right here. And in fact, we can use this as the limit definition of a partial derivative. So right now I'm going to write an approximately equals because I'm not going to take a limit quite yet. But knowing that delta r is very small, it's some very small but non-zero number, this is pretty close to the partial derivative of t with respect to r. Similarly, over here, I'm going to do the same thing. I'm going to multiply this time by delta t over delta t. And again, the thing that I've circled here looks a lot like what you have seen in previous calculus courses for the limit definition of a derivative, right? It looks a lot like f of x plus h minus f of x over h. And you guys know from your previous calculus course that if h is a very small number, then it would be fair to say that f of x, or f prime of x, is approximately equal to that. Now, in the limit, they're going to become equal, but for a very small h, they're pretty close to each other. Same thing here, but now with partial derivatives. And the reason we're talking partial derivatives here is you could see, let me switch to a highlighter here. I'm only doing the plus delta t in this t slot right here, right? So this is a partial derivative with respect to t. In contrast to last year's calculus course where we were able to use prime notation because we only had one variable of interest. So anyway, long story short, what I have is that these vectors that span this parallelogram could be described pretty well by some partial derivatives here. So there it is. Now, in the limit, this is going to become inequality here, but for now, these partial derivatives describe these 2 vectors very, very well for small enough delta r and small enough delta t. All right, so at this point, you might be saying, okay, Mr. Grotoni, I'm following all your steps. However, I'm not buying that this makes sense, right? Because what you're doing is you have this sector in XY space, and you're saying, let's approximate that area using a parallelogram. How do I know that that is actually a valuable thing to do? Because they didn't overlap perfectly. And what ends up happening, though, you can see it happening in this animation. So look what's happening here, lots of error. The difference between the parallelogram and the sector is large when that region is large. But look, the amount of error is now less as it shrinks down. The difference between the parallelogram and the sector is not very noticeable after that second step. And look, in this final step, you can't even tell the difference. In this animation, there is a um, a yellow parallelogram and a red sector, but you can't tell the difference between the two in the limb as you get very, very small. So for a large picture, you could see the error, but as our delta R and our delta T get really small, the error shrinks to zero. And really what we're saying here is that we can describe this well with a linearization. So there's a lot of cool mathematics behind this, but this is the general principle. B2 and B3 in the book have a really nice justification for why this happens. So I do want you to read B2 and B3 in the courseware in Casile to see that justification. But I have the same idea here, just kind of described as an animated GIF. You can see that as delta R and delta T get small, the difference between the parallelogram, the linearization, and the XY sector, that error shrinks to zero, which means that we're going to be able to do this with parallelograms rather than that original area. So look, lots of error, and then let's just watch it one more time. Now the parallelogram and the sector, very little error, very little difference between the two. And as delta R and delta T get small enough, look at this, it's amazing. It almost looks perfect. The error, the difference between the two is less than 1 pixel on my computer. All right, so now that we have that fact, now we are kind of motivated to say, oh, we're very interested in this orange parallelogram now. If we could find the area of the orange parallelogram for small enough delta R and delta T, that's going to do a very good job of telling us how much area we have in XY space after our transformation, after our mapping. So luckily, we have a way of computing the area of a parallelogram that's spanned by two vectors. And that theorem is as follows. You've seen this before, but the area of a parallelogram formed by two vectors v and w is the magnitude of the cross product of those two vectors. Kind of a nice little thing to use on math team, by the way. So if you ever do any competitive math, that's something that'll come up. So our XY area, our change of area in XY space, is approximately equal to the magnitude of the cross product of v and w. So let's use that fact. So I'm keeping my picture from the previous slide just so you kind of know the diagram that goes with this. But let's plug in for v and w. Here it is. Now, it turns out that this cross product, we could take scalars out of that. So we could take a scalar out of either vector in a cross product. That's a property of cross products. And remember, delta R is just some number that's really small, and delta T is just some number that's really small. They're both scalars. We could pull them out. All right, so now let's figure out how to take this cross product. Well, remember that my transformation, T of RT, was equal to X of RT, comma Y of RT. So the partial derivative here, dt dr, we could describe that as dx dr, dy dr. Now this vector only has two components, so for the third one, to make this cross product work, we have to put a 0 there to kind of embed it into three-dimensional space. And then dt dt, the partial derivative of t with respect to t. Now I'm going to take my x comma y, and I'm going to take the partial derivative of each component with respect to t, so dx dt dy dt, and 0. So it's a standard cross product. I just have to do a little bit of work here to understand what it means to take the partial derivative of a transformation with respect to r. It just means component-wise, look at each component and take its partial derivative with respect to r, or for the green one, t. And then since this is all in two-dimensional space, but a cross product lives in three-dimensional space, I'm just putting zeros here at the end to embed this all in three-dimensional space. Now, if you start computing this cross product here, if you start computing this determinant, then you get dx dr dy dt minus dy dr dx dt, and I can clean this up a little bit. That looks a lot like a 2x2 determinant to me, so I'm going to reduce that down to a 2x2 determinant. And here's the beautiful thing. Everything you see above is a really interesting derivation, but once it's been derived, you guys are going to get to use this for free for the rest of the chapter. You're not going to have to derive this stuff yourself. Now you see where it comes from and how it's done. But our job is now going to be to kind of formalize this little expression here, and then show you how to use it to make your change of variables work correctly. All right, so first of all, in the limit, now you guys see this happen in calculus all the time. We were working with delta r and delta t. In the limit, we're going to have dA is equal to this 2x2 determinant dr dt. And there's a name for this. It's called as a matrix, this guy's called the Jacobian matrix. And as a determinant, we call it the Jacobian determinant. Now, there's something interesting in the literature. There's an inconsistent reference to what is just the Jacobian. Sometimes when someone says the Jacobian, they mean the Jacobian matrix. Sometimes when they say the Jacobian, just that single word, they mean the Jacobian determinant. So I'll try to be careful here and always call this thing the Jacobian determinant. That way I'm being precise with language and I don't confuse anybody. But if you read any other sources and someone's just talking about the Jacobian, it's unclear if, you'll have to figure out from context whether they mean the 2x2 matrix just as a matrix, or whether they mean the determinant of this 2x2 matrix. Now, what did we just come up with? What we have is a little function here. We call it the area conversion factor in the U of I courseware, in the NetMath courseware. You won't really see that phrase anywhere else, but I like this name because it really tells you what the Jacobian determinant does. So the Jacobian determinant is an area conversion factor that allows us to compute an xy space integral in RT space. So it's an adjustment factor that adjusts for the fact that our mapping between RT space and xy space is not area preserving. Remember, that was the core problem. It's been 38 minutes that we've been talking about this now, but we should try to bring ourselves back to the original problem we were running into. We wanted to do an xy space integral, and we moved it over naively to RT space, thinking that it was going to make the problem easier, and we got a wrong answer. And the thing that we had not accounted for at the beginning of the video is that when we map between xy space and RT space, that mapping is not area preserving. So the area calculation that we did in RT space did not reflect what was happening in xy space. And what all of the stuff we just did over the past 20 or so minutes, all of this machinery, what it's designed to do is make that adjustment for the fact that our mapping, our change of coordinates, our parameterization is non-area preserving. This little guy right here, this 2x2 determinant, is an adjustment factor that adjusts for that fact. So what you guys are going to do from here on out is when you're trying to do a double integral in xy space, and it seems like xy space is not the right way to do it, you decide you want to map to some other coordinate space, some RT space that is more conducive to the shape of your region. Well, go ahead and do your change of variables, come up with your x of RT and your y of RT. Typically it'll be a parameterization of your region. A parameterization really is a mapping between an RT space rectangle and your xy space region. And that's fine to do that change of variables as long as we incorporate this area conversion factor. Actually, it's the absolute value of our area conversion factor um, into our integral, our adjustment factor that allows us to move over to RT space without any difficulty. Now, there is a reason that we have those absolute value bars there, and we'll talk about that in a second. So what you have to remember is that we derived the area conversion factor as the magnitude of a cross product, the area of a small little parallelogram. And since we want area to be positive, when we're doing this calculation in our double integral, we want to make sure that this area conversion factor stays positive, so we put absolute value bars here. Now, in a lot of cases, the absolute value bars will kind of fall off because you can look at how the problem's set up and you know that your area conversion factor will always be positive and you don't run into any issues. Other times, when you're writing your code in Mathematica, you might want to put absolute value bars there to just have Mathematica take care of the issues for you automatically. All right, so now we're ready. It's been a while, but now we're ready to fix example 2, what we started with at the beginning of this lecture 40 minutes ago. So remember, we wanted the area of a circle of radius 4 centered at the origin. Now, what we did is we came up with a clever change of coordinates. Our change of coordinates is really just a parameterization for this circle. A parameterization is our map between an RT rectangle and, in this case, our XY circle. Now, we want to compute our area conversion factor because that's what's going to allow us to fix this calculation. Now, our x coordinate is r cosine t, and our y coordinate of this transformation is r sine t. So to fill in this 2x2 matrix, all I do is I say, okay, I'm going to take r cosine t, my x, and I'm going to compute dx dr and dx dt. Well, the partial derivative of r cosine t with respect to r is just cosine t, and the partial derivative of r cosine t with respect to t is negative r sine t. Then I'm going to repeat for my y coordinate for my r sine t. So dy dr is the partial derivative of r sine t with respect to r. I just get sine t. And then similarly, my dy dt is the partial derivative of r sine t with respect to t, and I got r cosine t. I need to compute that 2x2 determinant, and I get r cosine squared plus r sine squared. You guys know the Pythagorean identity, so that just comes out to r. This is the Jacobian determinant. This is the area conversion factor for polar coordinates. This factor is something that we could throw into our double integrals in order to do our xy integral in RT space. If you throw that r into your integral, that'll allow you to do your xy integral in RT space, but still get a result that describes the area or the double integral that you were looking for in xy space. So let's do it. So here I have it set up. So here's my xy integral that I wanted to compute. And now we just set it up the same way we did at the very beginning of this PowerPoint. Look at the limits of integration. Look like it describes a rectangular region, and it's because it is. This is a rectangular region in RT space. Now I've corrected here by putting in my area conversion factor. I didn't put absolute value bars on it because I know that as r varies from 0 to 4, I know that r stays positive, so absolute value bars are just excessive in this case. For different sorts of changes of variables, more necessary. In this case, I don't really need to worry about it. All right, so now just start computing your double integral. You guys know how to double integrate. And oh my gosh, it took us 44 minutes and 22 seconds, but we did it. We have 16 pi. That is the area of this circle in xy space. And we did it using a change of coordinates to do a double integral in RT space. All right, so at this point, you might be asking yourself a very important question, which is, why would you ever want to do this, right? It took us 40 minutes to compute something that we could have done with pi r squared. But what you have to remember is I had a much more simplified example here than what you guys are going to be computing. So typically, your integrand is not going to be 1. And if your integrand is not 1, then pi r squared is not going to do the trick anymore. So now remember, there's all sorts of calculus computations that we can do, a double integral over a region in xy space where we're double integrating a function instead of 1. So not an area calculation anymore. And suddenly, this is a really useful tool. And the other thing to remember is now that we have this Jacobian determinant for polar coordinates, this is a freebie. So this video was an investment in the rest of the chapter because now you don't have to compute this area conversion factor again unless you're told that you have to. So everything on this slide you guys get to use for free from here on out unless you're working out a problem where you're told that you must, derive the area conversion factor for polar coordinates or something. That doesn't happen very often. Typically at this point now we just take it as a given that the area conversion factor, the Jacobian determinant for polar coordinates is r, and here's how we can compute our xy integral in RT space for polar coordinates. All right, guys, and just to wrap up here, my next 2 videos are going to be a bit shorter than this one, so that's good news. The basic idea is all we have left is to compute some interesting examples. So we have developed the machinery of the Jacobian determinant. We'll try some applications with some other interesting problems with polar coordinates, and then we'll try some other changes of variables. Try another change of variables for other situations where our region is not circular. We'll look at an elliptical region, we'll look at a region that's shaped like a parallelogram, some other stuff. Because none of this is specific only to polar coordinates. This idea of mapping between coordinate spaces, this idea of doing a change of variables works in a lot of different scenarios. All right, thanks so much for tuning in.